Ready na madam?
Sir, ready sir.
Start.
Very good morning children. Welcome to the webinar classes conducted by Tsrs&Jc, Hyderabad. This is Maths B, Coordinate Geometry, System of Circles, Class 3. Dear children, in this class, first we solve a problem. And this problem was also solved in the chapter Circles
Cartoons.
in the last exercise.
Mehndi Training Center with professional Mehndi designers.
Sir, Javed sir. Javed sir. आप म्यूट हो जाइए sir. Now we shall solve the same kind of the problem in system of circles also, but with a little difference. So how learning new topic helps us in simplification of the problems we have already studied. Now it is in a different method. Let us take the question, children. Show that the circle x is equal to x square plus y square minus 2x minus 4y minus 20 equal to 0. And h dash is equal to x square plus y square plus 6x plus 2y minus 90 equal to 0. Touch each other internally. Find their point of contact and the equation of the common tangent. Now, children, let us take the given circles. And now we shall prove that the two circles touch each other internally. For that, we need to revise the concept of the relative positions of circles. So, relative position depends upon the distance between their centers and the radii values, the sum of the radii and the difference of radii. We have to check the distance between the centers C1, C2 lies between which values. So, to calculate that values, we should calculate C1, R1, C2, R2, and R1 minus R2, R1 plus R2 using the given equations of the circles, namely x is equal to 0 and x dash equal to 0.
Snowy ho ya Hyderabad. Order kare biryani aaj hi starting at ₹149.
Bismillah walhamdulillah wassalamu ala rasulillah. Assalamu alaikum wa rahmatullahi wa barakatuh.
Alhamdulillah.
Kindly mute ho jaiye sir.
Bismillah today with the 6th lesson, which is the first lesson regarding the practical exercises on everything that we have learned up to now. Let us recap everything that we have learned up to now. One, we have learned something called
Madam.
Mute from your end. आप म्यूट करिए सर, वहां से साउंड आ रहे हैं. ओके सर, ओके ओके, नो प्रॉब्लम. So we shall find C1, that is center 1, and R1, radius 1 from the circle 1. What is the circle 1, children? X is equal to x square plus y square minus 2x minus 4y minus 20 equal to 0. The coefficient of x is minus 2. Half of that is minus 1. With opposite sign, it will be 1. Similarly, the coefficient of y is minus 4. Half of that is minus 2. With minus sign, it is 2. So the center one, C1 is 1, 2. Similarly, reading the values D, F, C. From from the circle equation and substituting in the radius formula r1 is equal to root g square plus f square minus c, we shall get r1 is equal to root 25, which implies r1 is equal to 5. Now, from circle 2, let us calculate the center. X coefficient is 6. Half of that with minus sign is minus 3. Similarly, y coefficient is 2 from the circle 2. Half of that is 1. With minus sign it is minus 1. Therefore, center of the second circle is minus d minus f is equal to minus 3 comma minus 1. Also, we calculate g, f, c from second circle now. And substitute in the radius formula the root of g square plus f square minus c, from which r2 is equal to under root of 9 plus 1 plus 90, which is 99 plus 100. R2 is root 100, which is equal to R2, which implies R2 is equal to 10. Now let us calculate what is R1 minus R2 as well as R1 plus R2. Modulus R1 minus R2, that is mod of 5 minus 10, minus 5. Or you can take 10 minus 5, which is bigger, that we will take because it is mod, it doesn't make difference if we change the order. Our aim should be, it should be positive. The difference of distances should be positive because distance is always positive. Now 10 minus 5, bigger number minus smaller number. So 10 minus 5 is 5. Now R1 plus R2. Now R1 plus R2 is 10 plus 5. So 15. Now let us find the distance between the centers C1, C2. C1, x2 minus x1 whole square plus y2 minus y1 whole square. C1 is x1, y1 and C2 is x2, y2. Then the previous center C1 is 1, comma 2 and C2 is minus 3, comma 1. So minus 3, minus 1 and this is minus 1 and 2. Now C1, C2 is equal to under root of minus 3 minus 1 is minus 4 whole square, which will be plus 4 when we square, 4 square, 16. Minus 1 minus 2 whole square, minus 3 whole square, when we square it is 9. So C1, C2 is root 25, from which it is 5. We have already seen that modulus R1 minus R2, 10 minus 5 is also 5. Now we have got C1, C2 is equal to mod R1 minus R2 is equal to 5. What does it mean, children? This equation or this condition shows that the given two circles x is equal to 0 and x dash is equal to 0 touch each other internally. One circle will be inside the interior plane of the other circle. Can you see the diagram, children? X is equal to 0 is completely inside the h dash is equal to 0, sharing a common point capital Q. That means the circle S is equal to 0 is touching the circle H dash is equal to 0 internally at the point Q. Now, our aim is, the question is not yet over. Now, our aim is to find the point of contact, that is the coordinates of Q, as well as the equation of the common tangent of x is equal to 0 and x dash is equal to 0 at this point Q. Now, in the chapter circles, we used to find this Q and then substituting Q using the formula x1 is equal to 0, we used to get the equation of the common tangent. But if you observe, this common tangent acts as a radical axis also, as we have learned the new concept radical axis here. When the two circles touch each other, the tangent itself becomes the radical axis. When the two circles intersect, common chord will become the radical axis. When the two circles touch each other, the tangent will become the radical axis. A radical axis will become the tangent. This enables us to find the equation of a tangent in a simpler form simply by x minus h dash is equal to 0. Because the equation of radical axis is x minus h dash is equal to 0. The difference of the two circles. The difference of the equations of two circles. Now we have what is s from here and we have h dash minus sign. So it is minus x square minus y square minus 6x minus 2y plus 90 equal to 0. On cancelling x square and minus x square, y square and minus y square, we will be remaining with x terms, y terms as well as constant. minus 2x minus x minus 8x minus 4y minus 2y. This is minus 6y and minus 20 plus 90, which is plus 70. Taking minus 2 common, we shall get 4x plus 3y minus 35 equal to 0 as the equation of the common tangent at Q, or is the equation of radical axis. Now, we find the point of contact. The point of the contact Q divides the line joining the center C2 in the ratio of their radii. R1 is to R2 is 5 is to 10. In simplified fraction, R1 is to R2 is 1 is to 2. When the circles touch each other internally, we observe the point of contact is external. Therefore, the point of contact Q is obtained by using formula R1x2 minus R2x1 by R1 minus R2, comma R1y2 minus R2y1 by R1 minus R2. Substituting R1, R2 as 1 is to 2. 1, 2. Wherever R1 is there we substitute 1, and wherever R2 is there we substitute 2. And here x1, y1 are from the x coordinate of the centers of two circles. Y1, y2 are from the y coordinates of the centers of the two circles. On simplification of which we get the point of contact as 5, 5. So we have shown that the circles touch each other internally, and we have found what is the point of contact, and we have also found what is the equation of the tangent, common tangent at that point. Now we shall discuss one another important concept, the last concept of the system of circles. Dear children, in this concept, first we shall consider the three circles. The circles, look at the diagram, children, the darkly outlined circles. Suppose the first circle is x equal to 0, and the second circle x dash is equal to 0, and under that, the third circle is x triple dash is equal to 0. X dash, x double dash, and x triple dash equal to 0. These are the three circles whose centers are non-collinear. The centers are not on the same line. The centers of all these three circles are not on the same line. And no two circles of these are intersecting. See the diagram, children, it's a rough sketch. No two circles of these three, the darkly shaded outlined circles, first circle, second circle, and third circle are not intersecting. Then circle having radical center of these circles as the center of the circle. That means first we have to find out the radical center of x dash equal to 0, x double dash is equal to 0, x triple dash is equal to 0. We shall get the center. And then length of the tangent from the radical center to any of these three circles as radius. Now let us take any of these circles. Suppose x dash is equal to 0. And then we have to find out the length of the tangent, from where the length of the tangent is found from an external point in the last case using root x double 1. That value should be found to any of these three circles, x dash equal to 0, x double dash is equal to 0, or x triple dash is equal to 0 from radical center using root x double 1, either from this circle or using this circle or using this circle. We shall find out root x double 1. Then that root x double 1 will be the tangent, radius. That root x double 1 will be the length of the tangent. That shall give us the radius of the circle. So taking the radical center as the center and this length of the tangent as radius, we shall find the equation of the circle. That is this circle. On the top we have. What is this circle do? What this circle do is this circle cuts the given three circles orthogonally. See children, this is x dash, this is x double dash, and this is x triple dash. Our circle, now new circle, will cut the first circle This circle will cut the second circle, and this circle will cut the third circle. How does it cut? It cuts orthogonally. That we shall prove now. For that, let us take the center. Let C be the radical center. Because the required circle center is radical center, let us take C be the radical center of the three given circles. As no two given circles of three circles are intersecting, the point C is exterior to this circle. Okay, the C lies in the exterior plane of the given circles. It neither lies in the first circle, nor in the second circle, nor in the third circle. What enables us to conclude this statement is the centers of three given circles. The given circles are not intersecting. When they are touching, the point of we cannot assure that radical center lies outside or inside. It is on the common tangent. And when the circle is intersecting also, it can be on common curve. As per the definition of the radical center, it will be clear if the two circles are non-intersecting, then C will be exterior to these circles. The locus of all the points which satisfies the powers with respect to the first circle and with respect to the second circle are equal, from which we'll get radical axis. So that enables us radical center in this case lies outside. Therefore, we can conclude the point C is in the exterior to this circle. Now let us take this C as origin. As the transformation of axis enables us to shift the origin to any point that we need. Let us take this as origin. Let the equation of these three circles be h dash is equal to, we'll take in the general form of the circle, taking g dash, f dash, c dash as x, y and constant. X coefficient and y coefficient and constant children. Similarly, we will consider h double dash and h double dash. Now, these are the three circles in the general form. Now, what shall we do? We shall find the length of the tangent from C to 2 and 3. What is the length of the tangent? Root h double 1. Because root h double 1, because writing root here is difficult, I have taken this as power 1 by 2 children. Power 1 by 2 and root are one and same. The length of the tangent from the center to circle 2 is root c double dash. Because it is origin, we don't have now any other term. H double 1, x1 square plus y1 square plus 2gx1 plus 2fy1 plus c. And c will be free from x and y. Therefore, only this term remains. Because it is circle 2, we have it is c double dash under root. When it is circle 3, we have under root c triple dash. The lengths of the tangent from the radical center to these circles are equal. Because the radical center is equidistant from all the circles. Therefore, we have c1 power 1 by 2, that is root c dash is equal to root c double dash is equal to root c triple dash. This is very, very, very important point that we need to observe, children. Therefore, squaring on all sides, c dash is equal to c double dash is equal to c triple dash. Dear children, our circle is centered at origin and radius is the length of the tangent. You can take any of this as radius. All these values are one and the same. Let us take c dash as a radius and 0, 0 as a center. What will be the relation, children? Here we have a conclusion that c dash and c double dash and c triple dash are drawn from an external point. Therefore, under root these values are positive. Now the equation of the circle having the center as c and the radius as root c dash, we have the equation x minus h whole square plus y minus k whole square is equal to r square. What is r, children? C dash power 1 by 2. When it is square, it is only c dash. Now we prove that this circle, whatever we got in equation 4, x square plus y square minus c dash, is orthogonal to the given circles 1, 2, and 3. How can we prove? By checking the orthogonality condition. 2gb dash plus 2ff dash is equal to c plus c dash. Now let us apply the orthogonal. Now we shall prove that our circle 4 is orthogonal to first circle, is orthogonal to second circle, as well as is orthogonal to third circle. This is what our aim. Now what is the condition of orthogonality? 2 times gb dash plus ff dash is equal to c plus c dash. Now we substitute G, F, C are from the first circle. This is C, children. By mistake it is written C dash here. G, F, C are from the first circle. Our circle 4. Okay, it is C dash only. Our circle is centered at 0, 0, therefore 0, 0. And C dash is same as C dash for our first circle. And fourth circle. We have taken length of the tangent as C dash in this case. So it is minus C dash for the fourth circle as well as first circle. Now G dash, F dash, C dash are from the circle 1. H dash is equal to 0. Look at the left hand side, children. 0 into something is 0, 0 into something is 0. Therefore left hand side is 0 and right hand side the same equal values with opposite sign gets cancelled. 0 equal to 0. Hence, the condition of orthogonality is satisfied between the circles 1 and 4. Therefore, the circles 1 and 4 are orthogonal. And let us check the same condition between the circle 2 and 4 now. Same condition. But left hand side we substitute the values G, F as 0, 0 and G double dash, F double dash as it remains same. But look at the right hand side, children. It is minus C dash plus C double dash. We have observed a condition where C double dash, C dash and C triple dash are equal. So substituting C double dash as C dash, we get right hand side minus C dash plus C dash gets cancelled. So LHS is equal to 0 is equal to 0. From which we say the condition of orthogonality is satisfied by circle 2 as well as circle 4. Circle 1 is orthogonal to circle 4. Circle 2 is orthogonal to circle 4. Now we shall prove that we can easily conclude. We need not prove now. In the similar way, we can also show that the circles 3 and 4 are orthogonal. Thus, the circles having radical center of 3 circles as the center of the circle. The circle 4 is obtained in a process of taking radical center as the center of central. And the length of the tangent from the radical center to one of these circles as radius. And we also observe that this circle 4 cuts the given 3 circles orthogonally. Now we shall solve the problem on this concept. Let us find the equation of the circle which cuts each of the following circles orthogonally. We have 3 circles like we had in the previous discussion, but these are not general. Some specific values are given for G and C. Similar in the same theory that we have discussed. Now H dash is given, H double dash is given, H triple dash is given. Let us take H dash as equation 1, H double dash equal to 0 as equation 2, H triple dash is equal to 0 as equation 3. Now we shall find a circle which is orthogonal to these 3 circles. The orange color shaded is the circle, is the required circle, and is cutting orthogonally the given circle. Is this rough diagram, children? The center of the required circle is radical center of the given circles, and radius of the required circle is the length of the tangent from this point to any of the given 3 circles. Therefore, to find the equation of the required circle, we will find the radical center as well as the length of the tangent from the radical center to any of the given circles. Now, to find the radical center, what shall we do? Radical axes are needed. How can we find the radical axis? Just by subtracting the equations of respective circles. If we need the radical axis of 1 and 2, we shall consider the equations of the circles and subtract their equation. The radical axis of h dash equal to 0 and h double dash equal to 0 is h dash minus h double dash equal to 0. On simplification of which we will get x minus y equal to 1. Observe children, x coefficient minus x minus 3x minus 4x, 6y minus 2y minus 4y, and constant 5 minus 1 equal to 4. Taking 4 common and cancelling on either side, we shall get x minus y equal to 1 as the radical axis of the circle 1 and 2. Similarly, we shall find the radical axis of 2 and 3. Equation circle 2 and circle 3 are known to us. Simply subtracting their equations, we shall get radical axis as 3x minus 7y equal to minus 1. X minus y equal to 1. We got equation 4 and 3x minus 7y equal to minus 5 as equation 5. Solving these two equations, we get their point of intersection as 3, 2, which will be the center of the required circle. Now solving equations 4 and 5 method is also described. The point of intersection of 4 and 5 is 3, 2. Now the length of the tangent from this point 3, 2 to the circle 1 is root h double 1. Instead of root, I have taken power 1 by 2 children. So substitute in the first equation. It is 3 square, x square is 3 square because our x coordinate of the point is 3 and y square is 2 square. In the equation it is 3x, so it is 3x1 which will be 3 into 3 and 2y1 2 into 2 plus 1. On simplification of which it is root 27. Thus, the required circle is x minus h whole square plus y minus k whole square is equal to r square, which is x minus 3 whole square plus y minus 2 whole square is equal to root 27 power 1 by root 27 whole square. On simplification of which we shall get x square plus y square minus 6x minus 4y minus 14 equal to 0 is the required equation of the circle. Dear children, with this we have completed our system of circles chapter. So we have completed the 2 chapter circles and system of circles in our coordinate geometry. And today's assignment is complete the exercise 2b. With this statement today, we can solve some of the problems of exercise 2b. Balakishan sir has explained some of the concepts yesterday, and today was the last concept with which you can complete the exercise 2b, children. As we finish the topic, let us revise the concept what we have learned in this chapter. Dear children, we have learned angle between the circles. We have learned that 2 circles will intersect each other if the distance between their centers lies between the absolute value of the difference of their radii and sum of their radii. That is, when mod r1 minus r2 is less than c1 c2 is less than r1 plus r2, the 2 circles intersect, and at that points of intersection tangents can be drawn, and angle between such tangents is the angle between the circles. And if theta is such angle, then we have got the value of cos theta as d square minus r1 square minus r2 square by 2 r1 r2. The d is the distance between the centers, and r1 is the radius of the first circle and r2 is the radius of the second circle. And we have also learned that cos theta is equal to c plus c dash minus 2g dash minus 2f f dash by 2 times root g square plus f square minus c into root of g dash square plus f dash square minus g dash as another important formula. Using this formula, we have defined what are orthogonal circles and conditions for the circles to be orthogonal. The 2 circles are said to be orthogonal if angle between them is 90 degrees. And the condition for orthogonality is 2g dash plus 2f f dash is equal to c plus c dash. After that, we have solved the problems related to these concepts, and we have seen if x is equal to 0 and x dash is equal to 0 are 2 intersecting circles, then x minus x dash is equal to represent a common third of these circles. And if the circles are touching, then x minus h dash is equal to 0 is a common tangent. So there exists a relation between a second degree curve and a first degree curve. X is equal to x square plus y square plus 2dx plus 3fy plus z equal to 0, and L is equal to Lx plus my plus n equal to 0. Suppose the circle is S and the line is L, then the linear combination of these two equations, namely x plus kl equal to 0, represents a circle. We have an equation of circle, children. We have also an equation of a line. The linear combination of these two, that is multiplying some constant with any of these equations and then adding this equation. What will be the geometric equation? Because the circle equation is a second degree equation. Line equation is a first degree equation. When we combine this, or linear combination of this results into a circle. But which type of a circle we get? We shall get a circle passing through the points of intersection of x is equal to 0 and L is equal to 0 for all values of k. That is, we have a circle first S and then we have a circle, a line L. When they intersect, we have 2 points in common. And we shall get a circle which is passing through the points of intersection of x is equal to 0. Suppose this is a x is equal to 0 and this is a line. Now this line is intersecting x is equal to 0 and h dash is equal to 0. So assignment, so we have s plus k equal to 0, ks plus ms dash is equal to 0 in such a way that our circle and line intersects in 2 points A and B, and we shall get a new circle from this family, x plus k equal to 0 for varying values of k. If you give k equal to 1 value, we will get a one circle. What will that circle do? That circle passes through the points of intersection of x and L. K equal to give another value, k equal to 2. Then we'll get another circle. Like that, we'll get infinite circles out of this family for varying values of k. Now, ks plus ms dash equal to 0 is also a circle. Which type of a circle? A circle which is intersected. Now we shall get now, are these two circles intersecting? Yes, they are intersecting. Suppose they are intersecting at 2 points. X is point P and point Q. Now we will get another circle which are passing through the points of intersection of these two circles. In the first case, this is x plus kl equal to 0. In the first case, it is x plus kl equal to 0. So first we have a circle, and then we intersect a line. The circle drawn is x is equal to 0, and now we have a line L is equal to 0. Are they intersecting? Yes. And now we will get infinite number of circles which are passing through the point of intersection of these two circles. So x plus kl is equal to 0 is also a circle, but circle which is passing through x is equal to 0, the points of intersection of x is equal to 0 and L is equal to 0. Ks plus ms dash equal to 0 is also a circle. Which circle? The circles which are passing through the point of intersection of x is equal to 0 and h dash is equal to 0. How many such circles exist? Infinite circles for varying values of this k. We get infinite circles in this family. For varying values of k and m, we get infinite circles in this family. So what are radical axes of the given circles? And definition we have seen, children. So radical axis is defined to be the locus of a point which moves so that its powers with respect to the two circles are equal. find the power of a point with respect to the first circle and with respect to the second circle. CP square minus half square. If that value are equal, collect all those points. The locus of such points is a line, and that line is called radical axis of given circle. If we have the circles are in such a way that whose centers are non-collinear and they are non-intersecting, then there exists three radical axes for the given three circles, and all these three radical axes are concurrent, and the point of concurrency of these radical axes is called radical center. And these radical centers will be equidistant from the given three circles. And we have observed that radical axis of two circles is a common curve when two circles intersect at two different points. And the same acts as a common tangent at the point of contact when the two circles touch each other. We have also solved some problems using this. And we have seen that the radical axis of any two circles bisects the line joining the points of contact of the common tangent to the circle. Dear children, we have solved the problems using these concepts. And the last concept that we have studied is how to find the equation of the circle which is orthogonal to given three circles. First, we shall find the radical center of given three circles and the length of the tangent from the radical center to any of these three circles, which gives us the radius. Using that center and radius, we shall find the equation of the circle. And we have seen that that circle intersects the given circles orthogonally. These are the concepts that briefly we have seen, and we have also solved the problem on this concept. Children. With this, we have finished our system of circles chapter. And what we are going to learn next, children? It is conic section. In coordinate geometry, we have circles, system of circles, and then conic section, under which we have the chapters parabola, ellipse, and hyperbola. So these three chapters, parabola, ellipse, hyperbola, come under conic section. And why these chapters are called conic section is very important, children. Not only these three chapters, in fact, circles, parabola, ellipse, hyperbola, a pair of straight lines, a straight line, and a point are called as conic sections because each is a section of double napped right circular cone with a plane. These curves have a very wide range of applications in a planetary motion, design of telescopes and antennas, reflectors in flashlights, etc. So, the concepts that you have studied in the circles and system of circles will help you in understanding the concepts of parabola, ellipse, and hyperbola. Please revise the concepts that we have studied in circles and system of circles well before going to the next concept, conic section, tomorrow. Thank you, children. With this, we end today's class. God bless you all.